Whereabouts are we? What topic is this?
I guess like I don't know, like modelling sine graphs, sine cos tan graphs.
Sure. They are using a model. They're modelling with an equation. It's a differential equation, so we might wonder if we need to solve it.
Yeah.
And it looks as though h equals that stuff in part A is the solution. So they're saying solve this differential equation. Solve in the sense of solve for h. Now you might say, actually, you could get everything in terms of h. Sorry, you could get h in terms of everything else. You could very quickly make h the subject of that, which is fine, but it wouldn't be completely in terms of t. So what they're saying is, try and make h the subject of this equation in such a way that it's completely in terms of t, and you've got rid of the derivative there.
Right. Okay.
Okay. Now I don't know how much. I mean, we may have done plenty, but I can't recall if we've done solving this kind of differential equation. Or you may not have broached it yet.
Well, okay. Well, to get h on one side, what are we gonna put instead of the dh over dt?
Exactly. Yes. Well, by putting it like that, we are doing the first stage. We are going to put h on the left-hand side with the dh at least, and my personal preference is to put it with dh dt.
Okay.
And leave the dt on the left. Okay, so let's do that. Tell me what to write.
So bring the dh over to one side, over to the other side.
The dh?
Yeah, is that what you're saying?
No, I'm saying let's leave that alone.
Yeah.
In fact, this process is called, not to give the game away, but perhaps you're going to say, well, of course we've done this. Have we done separation of variables? So called?
I don't
By that
remember
name? Maybe not. No.
Fine. By that name, at least.
I mean, you could see why it's called that insofar as, you know, we're getting h on one side. We've still got this derivative to get rid of. Part of the method as generally taught is to put the dt around the other side, which is just a kind of mnemonic device, really, and is beside the point. So what I want to do is take the h over to the left-hand side.
Okay.
Together with that.
You couldn't do that until you got rid of the 40. Would take the 40.
Yes, we could. Sure, we could. We could take this h round to the left-hand side, couldn't we?
Wouldn't you have to take the cos 1.25t as well?
Why? How are you passing that fraction? What would be the other ways of writing it? Surely one of the other ways of writing it would be h times the rest of the fraction. So I don't see why you can't take it around the other side.
Oh yeah, okay. Yeah, I suppose you, yeah. Right.
Okay.
So yeah, divide dh dt by h.
Yeah. But I mean, remember dh dt, yeah, all right, it is a thing. We could divide it by h. What would be another way of putting it that we just prefer, though? I mean, what's another way of saying divided by, which we usually prefer?
Of.
I mean, let's not make a bigger fraction is one reason I'm reacting against that.
Yeah.
How can we bring the h over here without doing that dreadful thing?
we could flip it and say dt times h over dh.
Could we? Would that be the same? I mean, or, well, it wouldn't have to be as long as we do the same to the other side, but that's drastic and consequential.
Oh,
But
okay,
what's
so
another way of accommodating h on the left-hand side other than that messy thing? What's another way of writing that?
dh over dth or hdt.
What, like that?
No, with the h on the bottom.
Right. Okay. Now what, okay, that is okay, you're saying there. That's nearly it. I just bridle at that as well, because, you know, we like to think of DHDT as a thing.
Yeah.
Let's try not to, I mean, we do sometimes use it as a fraction, but we prefer to avoid using, referring to it as a fraction if we can. I mean, it's a matter of taste.
You say 1 over h times.
Thank you, yes. I mean, it's like, how were you to know that that's what I meant? What an odd thing to do, what an odd way to put it, except it will come naturally, you know.
Yeah.
It's a preference that you will use.
Yeah.
Whether you're doing it my way or a slightly different way. Right, so we've got that on the left-hand side, and on the right-hand side, what have we got?
Cos 0.25t over 40.
Okay, and I do have a vague prejudice against saying divided by if I can write like that, really. Why is that? I wonder if I have if I can justify that prejudice. It's partly because of when we're integrating, people who, when they're integrating, end up dividing the integral by something instead of choosing the new coefficient. Are usually having trouble. Right. So we turn, first of all, we turn that into that, and that's called separating variables.
Yeah.
Some people would disagree and say, I haven't quite separated the variable until I've taken that dt over here instead. And they think of that as multiplying both sides by dt. You'll be told to do that in class probably, but you can take it with a pinch of salt. Let's not bother. Right, so what we're trying to do you remember yesterday, did I open yesterday's? Because we were definitely doing implicit differentiation, weren't we?
Yeah.
Here's where we did it. And you needed persuading because you wanted to make y the subject and then differentiate. And you'd forgotten about the easy benefits of implicit differentiation, even if you don't have to. But sometimes you have to, and whether you had to or not, what you end up with is a derivative in terms of y as well as x, isn't it?
Yeah, yeah.
So by the same token, if you started off with this differential equation, dy dx equals that, you've got your work cut out integrating dy dx to get y.
Okay.
Why? Because your derivative is in terms of y as well as x. If you had dy dx as an explicit function of x, then you would say, okay, I just have to look at this function of x and see how to integrate it. By the way, you know how if I'd written f dashed there then I could have written just ordinary f there, couldn't I?
Yeah.
But if you have written f there instead of f dashed, you can call that capital F. That's just a convention.
Right.
But I don't know why I didn't call that f dashed of x, because that's what we usually call dy dx, isn't it?
Yeah.
The trouble is, yeah.
Well, so capital F equals F dash. Is that what you meant?
The
The
derivative
opposite.
of capital F is f.
Okay.
The derivative of f is f dashed, so that would be further down. That's the next level down. I'm just saying, if you find yourself in a bind because you've written f for some reason, I didn't really have a good reason. I should have called that f dashed and called that one f. Oh, this is all beside the point. You won't hardly ever come across f meaning integral, capital F meaning integral. But anyway, the point is, if we've got an explicit function of x, we'll see how to integrate it, won't we? But remember, all the integration problems we've been doing have at least been explicit functions of x.
Yeah.
They haven't had y's in them.
Yeah.
But what we've got here, because it probably has been the result of an implicit differentiation or for whatever reason, what we've got here is similar to this situation here, isn't it? We've got a derivative in terms of both x and y, or in this case, in terms of both h and t.
Yeah, only that was the answer to the last one, and now we're starting with it.
Yeah, right, that's right. Now, you know my habit of implicit differentiation was going from that level down to that level. Whereas here, I'm going from this level up to that level because it's backwards, like you say.
Right, okay.
Okay, so that's my big picture, which I don't frequently enough signpost because, anyway, right. So we want to get back up here to find the solution of this differential equation. Well, a bit like with implicit differentiation, where we were just prepared to have to employ the chain rule, that's what we're going to do here as well. We're going to employ the chain rule here.
Okay. So
and say, as long as we employ the chain rule, because h is an inner function of t, further inside there you've got t, then we can differentiate with respect to t on both sides, can't we?
yeah, yeah.
Okay, which side would you like to do first with respect to t?
The left-hand side.
Okay, what are you guessing the left-hand side is with respect to t?
When we get ln h.
Excellent.
T.
Ln of h of t, yes. Yes, I
Yeah.
put that little t in there just to remind us that h is implicitly a function of t, we just don't know what. That's also another little shorthand. H of t being h equals a function of t. Sometimes the same with, sometimes instead of writing y equals, this is the usual thing, isn't it? Y equals function of x. Sometimes we just call it y of x as a shorthand.
Yeah, okay.
That's the liberty I was taking there. I was just saying h, which by the way is a function of t, hence the chain rule. Well, yes, the whole thing here is the derivative with respect to t of natural log of h.
How did you know to how do you know to do this? What we're doing right now?
Because the only kind of differential equation that you need to know how to solve is the kind that you can solve by doing what's called separation of variables, where this is the routine. You will have more than you want on the right-hand side. It might not be served to you on a plate, like this, you may have to form the differential equation sometimes. All right, and then you'll have to see how, oh, it's probably in this format. I can have the derivative on the left, and then I've got this something on the right. Of course, if it was purely in terms of t, then fine. You would just go ahead and integrate both sides and get h in terms of t, wouldn't you? But if you've got h mucked up in the derivative, just like y was mucking in with this derivative here, the derivative was mucked up by the y, getting whatever. Then separation of variables is what you want to do. Get the y's out of the what you'd rather was a function of x, get the h here out of what we would rather was a function of t. Because
know to integrate it.
Well, yeah, because we know that we're going to be able to use the chain rule on the left, and then the right-hand side is just its own problem. It might not be easy. This is fairly easy, although it does involve a chain rule aspect, doesn't it? Can you see how the right-hand side is also a backwards chain rule?
Possibly.
What's inner and outer of the composite?
The inner
is
0.25t.
Yeah. And the outer is?
Cos.
Yeah.
Or
a 40th cos, however you want to think of it. Because you're only going, basically it's cos. You only need to think basically, don't you?
Yeah.
So basically the integral is what?
Wait, the whole thing?
Basically, yes. But not the whole thing in the sense of finished product.
Wouldn't it be 140 sine?
Yeah. 140, although we sense that we're probably going to have to adjust it, of sine of the inner function.
Yeah.
Absolutely.
And then, so on the bottom, you'd then multiply by 0.25?
Yeah. In which case?
In which case, on the top, you'd have to, so times in by 0.25, that's the same as dividing by 4.
Now, you are occasionally fudging this step. You're right that this was a kind of unintended consequence of our first draft.
Oh yeah, then we need to do times by 4.
Yes, you need,
and then,
for this equal sign to be true, you need to cancel the effect of that here, like that.
And then times the top by 4.
Yeah, so really what we've got up here is what?
4 over 40.
In other words?
In other words, 1 over 10.
Yes. And then always try to remember to check. Say, okay, well, what would be happening here? I'd get a 10th cos of that times a quarter, which is what I started off with, which was, which is a 40th.
Yeah.
So in a way, it's a shame. Yeah, I shouldn't obscure that fact there. That is it's a bit better, isn't it? So this is what we actually have, and these two bits just cancel. And now we've basically solved it, except for what should we not forget?
Well, have we still not done something in the integration?
Yep. Have we checked by differentiating? Yes. We get a 10th cos of that times a quarter, which is a 40th.
Mm. Yeah, I'm not sure.
I just mean, sorry, but
Just see. Okay.
you know, it never goes away, that necessity of adding c when you integrate.
Yeah.
Notice that we've integrated both sides, so surely we should have plus d, say, plus another constant of integration on the left, should we?
Yeah, probably. Yeah.
Except
Um.
except this not unwanted, this constant can be anything.
Yeah. Wouldn't it? Yeah. Would it not be the same on both sides?
No, they could be
Oh.
anything on both sides. In other words, for any choice of c here and any choice of d here,
Mm.
when we differentiate, we'll get all of this, won't we? Because the derivative of c, whatever it is, will be 0. The derivative of d, whatever it is, will be 0. So they
Yeah.
will drop out on the way down. So these could be any numbers at all. It's important to understand. I mean, for example, when you put a plus c there, you're saying, okay, this function is like a curve, but the c specifying the y-intercept is giving me, just indicating all the infinite possible translations of that curve, higher or lower, isn't it?
Okay. Yeah.
We call that a family, which is kind of understatement because we mean an infinitely sized family of solutions. But the same thing is happening over here. We've got a family, infinite family of solutions. But that means that any one choice of C can take account of the D. In other words, you might as well just assume that C here already means C minus D.
Okay. Right.
You just don't need more than one constant. I could put it on the left if I preferred, but I'm putting it on the right.
All right. Okay. I don't understand.
So, so have we done it? Well, it's a bit different. We could say they've finished making H the subject, and we haven't quite. But we could, from there, go to saying H therefore equals what?
H equals H equals how do you get rid of a learn
Yes. How do you get rid of a log?
um
So, for example, log.
you do log of the other side, wouldn't you?
No, because log of log doesn't cancel the log. Log of log is a thing. I
What do
mean,
you use?
it's like squaring a square. You want to do the reverse of log. Now, what is the reverse of having a log? So supposing we're saying x equals log 3,
Is it
and we want to say 3 would be what then?
1 over x?
No. Have to remind ourselves what log means.
Log
What's the
means
form of words?
e to the, what do you raise e to get 3?
Exactly. So
So
3 is
it's
what we get
x
when we do what?
e to the x.
3 is e to the x, therefore. Yes.
So
That's how to cancel a log, by saying,
e to the power equals.
by doing this, look. By saying e to that side equals e to that side. And saying to yourself, oh yes, of course they cancel.
Right, so e to the 1/10 sine 0.25t equals h.
Yeah.
Right.
The whole of all of that, yes. And we could make that look a bit neater. And by the way, don't forget, it's the whole, you're raising e to the whole of that. So I didn't put plus c down here. It's in that power up there.
Right, okay.
Is that what they've got? It's a lot closer. We've got the 10th there. But they haven't got the plus c, but they have got a 5. What's happened?
Why have they got 5?
Can you see where they got it from?
5 meters above the ground
When?
at the start of the ride.
Which gives us a particular example that h is
H is 5 when
good,
t is 0.
in which case 0.25 of t is
0.
in which case sine of 0.25 of t is
0.
in which case a 10th of that is
0.
in which case e to a 10th of the sine is
1.
good. Although we're forgetting about the plus c, aren't we there?
Yeah.
So we can't quite do that. We could say what we've got is 5 equals e to the 0 plus c. In other words, e to the c.
But there's a 5 in front of the e.
Right. So what's going on here? We can put this together. It does lead to this conclusion, but we need to see how. Or we'll fail to, set out our work to convince them that we understand. So what we could have done straight away here before plugging in, what if we just looked at that and thought, that's an awfully big power. Can we expand it into, so that we've got a smaller power? If you've got the power of one thing plus another, you can expand, can't you? For example, e to the a plus b expands how?
E to the a brackets b.
No. Not if you meant that. Did you?
No. Well, no, I did, but now I see it. It didn't look right.
What would that be the same as? E to the a all to the b means
E to the ab.
e to the ab. Good. For example, 2 to the 3 plus 5 means 2 to the 3
plus 2 to the 5.
Let's test that. What's 2 to the 3?
6.
No.
8. 8, sorry.
2 to the 5?
2, 4, 8, 16, 32.
So 1 plus the other is?
32, 40.
But what's 2 to the 8?
More than 40.
More than 40, yes. Okay. I mean, go on, find 2 to the 8. It won't. It's good practice. Because powers of 2, you want to become familiar with them. whenever you have the opportunity, get more familiar with powers of 2 or powers of small numbers in general. Go on, find 2 to the 8.
256.
Good, well done. So a lot more than 40, yes.
Yeah.
So, but how can we expand that into something or other?
2 to the 3 plus 5 is the same as 2 to the 8. I don't know.
Well, yeah, clearly that's the same as 2 to the 8. But what's a different way of, I mean, what is it in terms of 2 to the 3? Maybe it's not helping having a definite number 2. Let's just say 8.
Well, 2 to the 3.
X to the
Oh, yeah, 2. So like 2 to the 3 squared.
Oh. That would be 2 to the what?
2 to the. That would be 2 to the 6.
That would be 2 to the 6 because of that, which is because it would be 2 cubed times 2 cubed, wouldn't it?
Yeah.
But this would be x to the 8 would be x cubed, followed by what?
Times x to the 5.
Yeah. So what we wanted here was?
A multiplication times 2 to the 5.
And what we wanted here was?
Times e to the b.
And therefore what we want here is?
E to the 10th sine 0.25t times e to the c.
Yes. In which case, we can see that's how we determine the constant here. In fact, we don't need the constant itself. We're more interested in e to the power of that constant.
Right, okay.
And finally, we've got h equals what?
Where's h equals 5?
Well, that was in a particular case at the start, but in general, for later values of
h equals e to the c. No.
What's h in terms of t in the end?
Isn't it all of the other side?
Right, but now we can state that as being more completely.
I don't know. I don't see how it's changed. H to the
H equals, in general, what? Now that we know what e to the c is.
5 times e to the 10th sine 0.25t.
Which is what they had. Okay.
Yeah.
So, you know, this is what it's all been leading up to, really. A-level maths. Solving a differential equation. It's kind of the, you know.
Is it? Yeah.
That's what you're trying to achieve, really. Solve a differential equation. That sounds like proper maths, doesn't it?
Yeah.
Because differential equations are what crop up in physics and other stuff.
Yeah. Do you get them at A-level physics? Do you have to
Oh
do
yeah,
this?
the most famous one being, of course, F equals ma. That's a differential equation. Whether it's a good example, I don't know. But anyway, yeah, physics is all about solving differential equations. So are other sciences, I guess. Yes. But in physics in particular, they did seem to, most of the last few hundred years was about experiments leading to differential equations. And then the task was to establish what one variable was directly in terms of another without the derivative being there. So getting from this level up to that level is a useful thing to do. State the maximum height of the passenger above the ground. I think you know how to do this.
State the maximum height. Yeah. So wouldn't you set? Let's think. The cos bit to 1, because you know that's the highest it's going to reach.
Cos bit.
So cos 0.2. I can't see the equation, but whatever we finish with, sine.
Or what we finished with was
Oh,
this.
it's right there. Yeah. So set sine 0.25t to 1.
Yes.
And then 0.1 times 1, 5, it would be 5e times 0.1, wouldn't it? 5e to the power of 0.1.
Yeah. I'm just checking. I was just wondering, yeah, it shouldn't have been that difficult for me, but perhaps I was confusing it with a negative power, I was thinking, oh, wow. For smaller values of sine, could that lead to a larger value of e to that power? No. No, you're quite right. We want the largest possible value of sine to get the largest value of e to a tenth of that. So yeah, and you're saying, so your answer was again, give me it.
5e to the 0.1.
Yeah. Great. Okay, and the passenger reaches the maximum height for the second time t seconds after the start of the ride.
Okay.
Find the value of t.
So
we've got here the function. So we've got a choice between, the same as yesterday, a choice between, but we can have both. This kind of story, because it's sine, isn't it? So it is going to start with a t value of 0, where the sine part of it is 0. Oh, and by the way, yes, e raised to yes, what's the minimum value going to be?
We're 0.1 times minus 1, so 5e to the minus 0.1.
Yeah. Well, yes, well done. It's going to be taking it down below 1. Well done. Yes. But it is going to be starting at an intermediate value of 1, indeed.
To do this last bit,
or rather
what you do.
That's exactly the same. Look, sorry to interrupt. It's the same. It's a very similar situation, even though it's e raised to a power. We nevertheless are, like yesterday, we're starting at 5 and then going up and then down. But the shape of the wave will be different because of the power going on here. But we are starting at 5 again, aren't we?
Yeah.
Right, sorry, what were you going to say?
to do this last one,
Yeah.
couldn't you, once we figured out what 5e to the 0.1 is, like I suppose you put that in your calculator, and then you could just rearrange it to find out what t is. Wait, what is t? What is
You
capital
could say what we've got here is e to the 10th, all raised to the power of the sign, but the 5 isn't being raised to that power, so you'd have to be careful. But it's good that you're looking inside there and passing it in various ways. So basically, if I could just say, if I could just sketch very roughly, the roller coaster starts at what height?
5 meters.
At 5, yes. Wow, 5 meters, that's quite high up. Given that the passenger is 5 meters above the ground at the start of the ride, but they do actually confirm that there, don't they? That's not just a, yes, we were concluding that from there, but of course we concluded that from that. So you have to go up 5 meters just to get on it, right? And then surely you go from 5 times e to the 0 up to 5 times e to more than 0. So you are going up before coming down. Is it actually going to be periodic indeed? Yeah. I don't think we have to, yeah. I don't know how unrealistic that, let's see how unrealistic that is, what I'm failing to take account of there by cheating here. 5 times e to the power of 0.1 sine of 0.25 x, we'll call it in case they care. Right. Is it periodic? Zoom out. We'd like a more pronounced, we'd like, how can we change the y?
Is it just a much more shallow line? Like
Well, yes,
curved?
yes. I was just trying to change the scaling of the y. Yes, we do that here, don't we? If we make that a much smaller number, up to a much smaller number there, then we get a more pronounced aspect there, and we can see that it is perfectly periodic. Yes, just like a sine wave, pretty much. Starting at 5, going up. Yeah, yeah. Interesting. Right.
We could say that whatever we got as our answer to question B, can't you just add? So we know however many
Yes.
seconds that, just add like
Well, we got the
300,
maximum height. Here, they're not worried about the height.
but find out what t
Yes,
was.
absolutely.
Yeah.
Yes. And notice that that's like going around the unit circle from 3 o'clock, finding at what time you get to the top. Now notice the time is like the angle times 4 really, isn't it?
Yeah.
So yeah, here is getting to 12 o'clock for the first time, and then carrying on round, you get to the top of the clock a second time here. But yes, if we find the time taken to get from 3 o'clock up to 12 o'clock, well, that's not going to be hard, is it? The value of t when we get up to the 12 o'clock mark, what do you reckon? Oh, have I lost you? Oh no, sorry.
No, I was the value of t when we get up to the, well, we know that sine 0.25t is equal to 1.
Yes.
So that
So yes, and sine of what equals 1?
sine of 90 equals 1.
Yes. But is it degrees or radians? How do we know?
It is.
If in doubt, choose radians, especially if there's calculus involved.
Right. Okay. So it's 2 pi.
What? Careful.
Because
12
it's,
o'clock.
yeah, but it's 0.25 2 pi.
Oh, I'm with you. You've already multiplied it by 4. Yes, you're saying a quarter of t is pi over 2, therefore t is 2 pi. No, great. Yes. So indeed, the time here is 2 pi.
Yeah.
And the time here, therefore, is
4 pi.
careful. What are you multiplying by?
Oh, of course not. So that was 2 pi, and it will be add, that's 10 pi.
Yes. Absolutely. Done. So another very meaty question.
Good.
Next. And basically, let me just quickly. What happened here? It was, if you think your differential equation looks implicit rather than explicit, you don't necessarily have to make it explicitly in terms of t, but you try and separate the variables so that you can solve in that fashion using the chain rule on the left-hand side. Or what you'll be told to do in class is take the dt over here, multiply both sides by dt, and then stick an integral sign both sides here, which is fair enough. Then you're saying the integral of that with respect to h, because that dt has disappeared, is going to be equal to the integral of that with respect to t, because you've got a dt there.
Yeah.
Same thing.
Okay.